All right, today we're going to start working on cubes and cube roots. And we'll start with the cubic y equals x cubed. I'm going to go ahead and refresh your memory from the beginning of the year where we introduced you guys to all of these functions. The cubic y equals x to the third power has the key points of 0, 0, 1, 1, and 2, 8. And that's because 0 cubed is 0, 1 cubed is 1, and 2 cubed is 8. Now with a cubic, you can also have negative values because a negative times a negative times a negative is a negative. So negative 1 cubed is negative 1, and negative 2 cubed is negative 8. So we get a function that looks like this. I'm going to go ahead and write those key points off to the side here so that you have those. That was negative 2, negative 8, negative 1, negative 1, 0, 0, 1, 1, and 2, 8. For the domain and range of this is an easy one because it is all real numbers. As it goes, comes from the left, it is coming from negative infinity, and it goes all the way to the right where it goes to positive infinity. So negative infinity to infinity. And this function is always increasing. As we move from left to right, it is always going up, so it is increasing from negative infinity to infinity. And then for decreasing, we would say never. All right. For our transformational form, and we've used this several times now this year, so you're going to use the same type of function. The only difference is the operation. So we just came from the quadratic, so that was a 2. We're moving into the cubics, so that is a 3 there in the exponent. The A, B, C, and D are all still in the same place, and they all still do the same thing. Vertical stretching and compressing on the outside of the operation, horizontal stretching and compressing on the inside of the operation, left and right, and up and down. A negative out here gives us a reflection across the x, and a negative in here gives us a reflection across the y. I'm going to go ahead and graph a couple of these with you so that we can look at how that works. For example, here, f of x minus 2, that means to the right 2. So we would take each one of those points and move them to the right 2. So our vertex value, that 0, 0, moves to the right 2, it's at 2, 0. The 1, 1 moving to the right 2 units is going to be at 3, 1, and then at 4, 8 will be the other one, and then we do the same thing for the ones that come on the other side. So we have moved this graph to the right 2. You should be getting really good at these transformations at this point. The next one here would be to the left 1. So I would take each one of those points and move them to the left 1. It's important you know those key points for all of your functions so that you can easily graph with transformations without a calculator. So there is our left 1. It doesn't change the domain range or the increasing and decreasing since those are all real numbers. On our values here that are on the outside, that would be up 2. And so I would take each one of these points and move them up 2. And there is our graph. Now remember, when you're translating, you are not changing the steepness of the graph at all. It is just taking each one of those points and moving them left, right, or up, down. On this next one here, there is a reflection across the x since that's on the outside part. And so we would take each one of those points and reflect them across the x. Now 0, 0 is on the x-axis, so it doesn't really go anywhere. But that point that was at 1, 1 is going to go to 1, negative 1. And that point that was at 2, 8 is going to go to 2, negative 8 because it reflected across the x-axis. Same thing on the other side, we get a point at negative 1, 1, and negative 2, positive 8. And so now our graph is coming from the top to the bottom there. In this case, the domain and range is not changed either, since it's still all real numbers from left to right. However, this graph is decreasing this entire time as we move to the right. So this graph, we would say increasing, never decreasing from negative infinity to infinity. All right. The ones that are a little bit harder are the ones that change the steepness of the graph. So here we've got a 2 on the inside of our function. When it's on the inside, that is horizontal, not vertical. So that's going to be a horizontal. And when it's bigger than 1, it is a horizontal compression. And that would be by 1/2. Remember that scale factor flips to get it. So in this case, I can't multiply the vertex times 1/2 because 0 times anything is 1/2, is 0, sorry. The next point over that's 1, 1, I can take that and I can compress it horizontally, which means I'm coming in from the side and squeezing in. And that is happening by multiplying the x value times 1/2. So instead of going to the right 1 and up 1, it would go to the right 1/2 and up 1. And instead of going to the right 2 and up 8, it would go to the right 1 and up 8. Same thing on these on the left. And so we get a really skinny cubic here. This is where we changed the way that it looks. So the translations just picked it up, moved it around. These actually changed the way it looks. We took it from the side here and squished it in. That's what a horizontal compression looks like. I'll go ahead and do the horizontal stretch as well so you guys can see that. We've got this 1/2 on the inside, so this is a horizontal. And this would be a compression. And again, we're flipping it for that scale factor, so that would be a horizontal, sorry, I wrote compression stretch. Horizontal stretch by 2. So in this case, we're going to take it by the sides here and we're going to pull out to the side horizontally, not vertically. When I multiply my 0, 0 times 2, that doesn't change anything, so I'm still at 0, 0. But instead of going to the right 1 and up 1, I would go to the right 2 and up 1 because I stretched it to the sides there. And then instead of going to the right 2 and up 8, I would go to the right 4 and up 8. I'm multiplying those x values times 2. And so here we get a much wider cubic because we took it from the sides and pulled this way. Notice that the y values are not changing. What's changing is the x. That's that horizontal. Horizontal stretching and compressing only changes the x values. So let's talk about those y values then. That gets changed when you have the 2 on the outside. So that is a vertical stretch because it's bigger than 1, so it's a vertical stretch by 2. The scale factor is that one here on the y values. And in this case, we would multiply our y values. So again, 0, 0 doesn't change, but instead of going to the right 1, we go and up 1, we go to the right 1 and up 2. Same thing on the other side. And then instead of going to the right 2 and up 8, we would go up 16. So it's going to be way up there. So again, we've made this a thinner cubic. We've got something that looks like this. That's because we took it from here and we pulled this way. So our y values are being changed, not our x values. This does look similar to a horizontal compression, but it depends on where that number is on what exactly is happening to our graph. All right, on the back here, we're going to look at our other parent function, the cube root of x. And so this one, I do want to show you how to put this in the calculator so that you're able to do that. For the x cubed, it was no big deal because instead of a 2, you would just put a 3 there like we were in the quadratic. But with the cube root, you want to go to the math button. So it's right there to the left of that apps or below the alpha, that math button. And then you go down to the cube root. Sorry about that. There's kind of a glare there. Let me see if I can fix that. That's worse. Oh, okay, right there. So it's got the cube root of x right there. So that's the one that I would want to push. and then it gives me that cube root there, and we can start putting it. One of the important things I'm going to go ahead and say here, if you're doing a left or right movement, so I put in x minus 2 here, it is going to stay under that radical until you take it out. So when you go do up 3, for example, you would not want to do this. That is still under the square root. So make sure that you're not doing that when you plug it in, because then that just gives you bad points for a simple error. You want to use the arrow key to get out of under the square root, and then do your up 3, where it's clearly not under the radical here. So make sure that you key that into your calculator correctly. Since we're here on the calculator, I'll go ahead and show you the table for it. Let's go ahead and delete these. So there's our parent function. I'm going to go ahead and show you the graph of that. Gosh, that glare is bad today. It's not working out as well as I'd like. Okay, there we go. There is our cube root function. Notice it looks very much like the cubic. It's just going sideways instead of up and down. And then if we go to our table of values, notice that there are negative values here. That's because you can take the cube root of a negative. You can't take the square root, but you can take the cube root. All right, so let's go back to graphing that on our paper here. The points were very similar to the ones that we just saw with the cubic. They're just the opposite. So -8, the cube root of -8 is -2, because that's what multiplies times itself 3 times. These are inverse functions, so that's the reason why you see that as well. And then 1, 1, and 8, 2. So 0, 0, 1, 1, 8, 2, -1, -1, and -8, -2. So there is our cube root function. Similar to the cube one, this domain and range is also all real numbers. It is going all the way to the left and right and all the way up and down. And then for the increasing, it is always increasing, even though it is going from side to side here. As we move from left to right, the graph is increasing. So it is never decreasing. So there's our cube, our important stuff about the cube root. For its transformational form, again, these are always going to be the same. The only thing that changes is the operation. So instead of having this inside the cube, we now have it inside the cube root. But your A, your B, your C, and your D do exactly the same thing. So for this first one, it goes to the right 2. So I would take each one of these points and move them to the right 2. It is not changing its steepness at all, so it's got the same exact shape, and it's moving the same way. We have just picked it up and moved it for the translations. I'll go ahead and show you the reflection one. So our points with the reflection, instead of being above the x-axis, they are below. So it would be at 1, -1, and 8, -2. And then same thing on the other side here. So it has changed my graph to decreasing. It starts up at the top and then starts to decrease as it goes to the right. And I'll go ahead and show you one of the vertical transformations as well, so you can see that. So for this one here, that is a vertical stretch by 2. And so each one of these points is going to be multiplied by 2. So instead of going to the right one and up 1, it would go to the right one and up 2, to the right 8 and up 4. Same thing on the other side. And so our cube root here has been pulled upward for that vertical stretch. It's important that you're able to graph those, and in order to do that, you really need to know those key points. So make sure that you've learned the key points so that you can graph them with the transformations. The last thing we're going to talk about on transformations here before we go on to our next topic is writing the equation from the words. You're definitely going to have this on the quiz and test, so it's important that you can do that. It says write the equation of a cube root. This right here is telling me what is the parent function. So I know that the operation is going to be the cube root of x. That's why they give you that piece of information. If it said the cube, then we would do x cubed to start with. Now we work backwards. That was reflected over the x-axis. Well, I know to reflect it over the x-axis, I need a negative on the outside, so I know I'm going to have that part. Horizontally compressed by 1/4. This is probably the hardest transformation you have to put back in. So horizontally tells me it's going to be on the inside of the operation. So I'm going to have that cube root there. And remember, this scale factor that they gave us came from flipping it when it was in the equation. So in order to put it back in the equation, we need to flip it again. So inside of my operation here, I am going to have a 4. And it is factored out, so we'll have parentheses there. To the left, 3 would be plus 3 on the inside, and then up 1. So there's our equation. We worked backwards to write it. You should always be able to read those transformations back. We know that the negative on the outside is a reflection across the x. This is the b value, and when we take it out of the equation, we flip it. So this is a horizontal compression by 1/4, which is what they gave us. Left 3 and up 1. All right, we have a couple more things here to talk about with the transformations. On this one, they've given us multiple transformations, so I want to make sure that you're able to graph that with multiple. We've got this negative out in the front. That's a reflection across our x. Then we've got a 1/2, and it is not inside the operation. It is outside. The cube is only on this part right here. So that tells me it is a vertical, and in this case, compression by 1/2. We've got a 3 on the inside there, so that is a left 3. And then on the outside, we have this 4, and that is a down 4. So you always want to get all of the transformations that you have. Don't just pick one or two. You've got to do every single one of the ones that are there. So I've got 4 different transformations I'm going to do. These two are not going to affect my vertex. Because it's at 0, 0, when I multiply 0, 0 times negative 1/2, it does not do anything. However, the left 3 and down 4 is. So left 3 and down 4 puts my vertex right there. Now you can individually do each point, but you can start from this point and know that the next point over is supposed to go to the right one and up 1. However, if it's been reflected across the x-axis and vertically compressed by 1/2, then it is going to go to the right one and down 1/2. And then the other side would be the same thing. Notice it's rotationally symmetrical. So that's why we get those points there. The next point is supposed to go over 2 and up 8, but it's reflected, so it's going to go down, and it is compressed by 1/2. So it's going to go to the right 2 and down 4, because that is the 1/2 of the 8. And so same thing on this side. And here is our new function. So there it is, graphing multiple transformations. You want to make sure you get all of the transformations done. All right, we are now going to switch over here to working backwards from a graph. So when you want to write the equation of a graph, the first thing you want to do is find that vertex. So here is my vertex. So I know that this has gone to the right 2 and up 1. Those are the transformations that are the easiest to see. Now you need to start working with the other ones. we see there's not a reflection because it's still going in the same direction as our parent function, and that's what you're comparing it to. Now with the parent function, you are to go to the right one and up one, but that is not where the point is. It is to the right one and up 3, and to the left one and down 3. So I know that it has been stretched. And so by this first one, I'm seeing that it's been stretched by 3. So that would be a vertical stretch by 3. And you want to go ahead and make sure that that is correct. So you go over to your next point, which should be 8 and 2. But it is not. It is at 3, 4, 5, 6. So again, it's been multiplied by 3, so we know that's the scale factor. And then we would write our equation working backwards. That's the cube root since it's side to side. In order to get it to vertically stretch by 3, I need a 3 on the outside. To make it go to the right 2, I need this minus 2 on the inside. And then to go up 1, I need the plus 1 on the outside. Your other option for finding that, and we'll do that on this one here, again, the first thing you want to do is find that vertex piece. So that's right here at -4, -6. So I know it's going to the left 4 and down 6. I can also tell that it's been reflected, but I don't have to worry about that one just yet. So to figure out what the other transformation is, since I see it's not going 1 and 1 like it's supposed to, I know that there's an a value, so I can just go ahead and put the a value there, and then put the transformations that I know. I know it's moved to the left 4 and down 6. Then to figure out this a value, I pick any other point on our graph, and so you want to pick a whole number. So that one right there looks like a good one. That is the point -5, -4. And I plug that in for my y. Now I've made that a one variable equation that I can solve for that a. I add the 6 to get it to the other side, and that gives me 2 equals a. -5 plus 4 is -1. Cubed is just a -1. I divide by -1, and we get -2 is equal to a. And so we solved for the a. So you can do it algebraically, or you can do it from the graph. If you can't see it from the graph, then do it algebraically, because that one never fails there. So that would be our equation working backwards from that point. All right, a little vocab for you here. We're going to talk about even and odd functions. And so it tells us that an even function is symmetric about the y-axis. So it reflects across that y-axis. You see the same thing on both sides. So this right here could be considered an even function because if I fold it on the y-axis, then this part right here would land right on top of the other. So this right here would be considered an even function. It is symmetric across the y-axis. Now we know reflection across the y-axis is a negative on the inside. So basically, if these two are the same, it is an even function. A lot of the books write it this way as well, so that's another way of writing it. For an odd function, it tells us here it is symmetric about the origin. That means that it would be flipped across the x and the y-axis. So right here, this right here is symmetric across the origin. My origin is right here, that's 0, 0. And if I rotated it right there, then this part that's in the first quadrant is going to land right on top of the part in the third quadrant. So this would be considered an odd function. This right here would be considered neither because it is not symmetrical across the y-axis or across the origin. So an easy way to determine if it's even or odd is definitely by the graph. If we looked at this one, if I rotated it across this point here, then this first quadrant would land right on top of the third. And so this is an odd function. These would be considered neither, since they are not symmetric about either one. Again, neither with this one. This one here is rotational, so I can rotate across that origin. This part would land right on top of this one, so this would be considered odd. Our absolute value function is symmetrical across this y-axis, so this would be considered even. Here's another one you've already seen, the quadratic, that would be considered even. Now let's talk about if they give it to you as an equation, because you're going to see that on the quiz or test. And so we said that to determine if it is an even function, it needs to reflect across the y. So we can see if I reflected this across the y, I'm doing this negative x. So I'm going to plug in a negative x for each one of these x's. And then I simplify that. Negative x cubed, remember, a negative times a negative times a negative is a negative, so we get 2x cubed. And a negative 3 times a negative x gives us a positive 3x. Now, those two are not the same, so we know that it is not even. That is unequal to f of x. So now we would want to try the other one. So we want a reflection across the x and the y. So I'm going to find f of negative x. Now we can really take a shortcut here because we've already done f of negative x. That's this one. So if I just want to do the negative, I would change the signs on this one. So it becomes 2x cubed minus 3x. That is the same thing as this. Those are both the same thing. So equals f of x. That tells me this is an odd function. So graphically, I can look at it, see, is it reflected across the y? Is it reflected across the origin, which is the x and the y? Algebraically, I test those two to see if it is equal to the f of x, then that's where we're going to determine whether it's even, odd, or neither. If it's not, neither one of those work. So we'll try another one here. I try and find that reflection across the y. Now this is squared. So negative times a negative becomes a positive. So this stays as 6x squared plus 10. These two are exactly the same. So this is an even function. Our f of negative x, so our reflection across the y, is exactly the same thing as our original function. So this one is even. All right, we'll try one more. I check that reflection across the y to test to see if it's even. I get negative x cubed minus 3 times negative x squared minus 2 times negative x plus 7. So I have changed each one of those for a negative x. That is going to give me a negative, so we get negative x cubed. This is going to give me a positive because a negative times a negative for the square. So that's going to give me a negative 3x squared. Negative 2 times negative x is going to give me a positive 2x, and then the 7 does not change. I compare that to my original, and it is not the same. So that is unequal to f of x, so not even. Now I test it to be odd. So in this case, I want the reflection across the x and the y. And since we've already found the reflection across the y right here, all I need to do is change the signs for this reflection across the x. So I get a positive x cubed, a positive 3x squared, a negative 2x, and a negative 7. Now, when we look at that right here, that is not the same as f of x. So this would be neither, since it is not odd or even.